Hello, everyone. First time in Japan. It's a humbling experience. Awesome country. Thank you, ScalaMatsuri organizers, for having me. Are you guys ready to learn about free? Why? Because it's cool, right? It's apparently a very hot topic. Everybody is talking about it. But the question is, why is it cool? For me, free gives all the best from functional programming, which is ability to write a modular code. And when I say modular, I mean a code that you can have within your program different concerns, but you can reason about those concerns separately. You can test them separately. You can have your user authentication here, and you can have your send money transfer here. And you can test your user authentication. You know it works separately. Same goes from the money account manipulation. And then you can reason about something more complex when you combine those two together. And that's what free gives you almost for free. So what is free? Basically, this is free. Or at least its type signature. So think of free, nothing else, as a program. If some method gives you a thing of this type, it gives you a program, nothing else. As any program, the program is constrained by the language, here language S. And once you actually run your program, it will give you a value. And that value is going to be of type A. And that's all it is to free. That's basically it. Thank you very much. See you. All right, demo. I have slides for demo, don't worry. Before we actually see demo, just a quick introduction to task from ScalaZ, because I'll be using task. So if somebody is not familiar with task, think of task as the same thing as your future. The only difference between task and future is that if you get an instance of future, the calculations are already running. You might have your value already, or maybe it's still being calculated, but it's running once you get that instance of future. With task, you get just a value, and nothing is running yet. You will need to call some method here. The method is called perform sync, but there are equivalent asynchronous methods as well. That'll actually start the computation. So think of it as a future, like a future plus plus, all right? Demo. So as I said, free is a program that is constrained by the language. So that's the simplest example. We're going to find a very simple language, which is input-output. So here we have our small language, a print line and get line. So print line representing printing. Oh, no, because it's a slide. But I can do it from here, and I can hopefully do some magic to make it bigger from time to time. Not really. Can you sit closer? OK. So unfortunately, I cannot really make it bigger. Crap. Or I can. Well, you just made it more challenging for me. But I mean, you asked for it. Yeah, no problem. Crap. All righty then. All right, we can do it as you want. Somewhere here. OK, let's do this. Big enough? Oh, stop clapping. This presentation is going to suck because now it's going to be live coding. So you asked for it. All right, so this is our simple language, input-output. If we don't go through all this other codes examples, you're just going to see the slides at maybe in the hallway or something. Anyway, so this is our language. And now once we have our language, it would be actually a cool idea to construct a simple programs out of that language, right? So we will introduce a utility functions here. Is that OK? Is that phone OK for you guys? Awesome. So we have two utility functions, which already gives us a program. So printLine gives us a program that will, well, print a line. And getLine will give us a separate program that gets us a line from the users, and we get that instance of that line, of that string. And we use this little lift f function from ScalaZ. It's do the magic. So it just takes our element of our language and lifts that into the program. If that seems weird, don't worry, we're going to get there. So now, once we have those little utility functions, since free is a monad, we can compose those functions together to create a little bit more complex program. Here, what we'll be doing is we will ask for a name, get a name from the user, and then print nice to meet you, whatever the username is. OK? Sounds cool? Well, let's try to run it. So I'll make it bigger, no worries. Big enough? OK. Is it big enough for you guys? Yes? No? Yes? OK. So if we actually run it, you will see that nothing happened. Why? Because we still need to interpret that program. It's just definition of what we want to do. We don't have yet an interpreter that will actually do the thing. So as I said, slides were nicer because I could just pretty much jump to the next slide. But there we go. All right, so what we need to provide is something we call an interpreter. An interpreter is a natural transformation. So natural transformation is that thing on line 16, input, output to task. If that seems scary, it really isn't, because what natural transformation is, so if you have natural transformation from F to G, it really is just a function FA to GOA. So what we're providing is a function that will go from input, output parameterized by some A to task parameterized by some type A. And that's really all there is to it. So what we're saying is, what should happen, what kind of task I should return if I will see print line, where our task will be just printing line to the console. What should happen if I want to get a line, where we will return a task that will fetch a line from the user from the console. Does it make sense, more or less? All right. So now once we have that interpreter and we have our program here, we can run our program with interpreter. And there's a convenient method called foldMap. Sorry. There's a convenient method called foldMap that's actually running the program. So it will give us a task of type unit. Why unit? Because our program was returning a unit. And as you guys remember from the introduction, task is not really doing anything yet. You need to run it. So here we're using method unsafe perform sync that will actually run it. So let's try to do it. What's your name? Nice to meet you, Pavel. OK. So it kind of looked nice. Even though it's doing simple stuff, and you might be wondering, well, it's just input-output, right? Go away. So the next thing you would like to do is test your code. Think of your program that you would write without using free. If you have a program, like an application that actually talks to the user through a console, any kind of terminal, how would you test it? Obviously, there are some magic. You can do reflection, all that, and kind of try to read whatever was typed into the console, or try to emulate the console. However, with free, you get the beautiful unit tests for free. And let me show you how that looks. So we have our program here, right? Defined here. This is our program. And now we want to test it somewhere. So this is our specification. So this is our test. And the only thing that I'm providing here is a different interpreter. The program stays exactly the same. What I want to have a different, what the difference is that I'm providing a separate interpreter. This interpreter is using mutable data structures, some input stack and some output list buffer. And in that interpreter, I'm just saying whenever user is printing line, just take that line and push it into that list buffer. If user wants to get a line, then pop whatever is on the stack, pop the next thing. So then our test might look like this. We will initialize it with an empty output. We will initialize it with an input that has a single value push. We will run our program with that interpreter. And what we want to assert are two things. Whether the whole input was red, so the input side is 0, and what is on the output. So I would like to see what is your name, and nice to meet you, Pavel. And you have your unit tests for free, which is kind of the best unit test you can get. There's no injections or any weird other stuff that you would normally see in those kinds of tests. No magic. You just provide a separate interpreter for your test, and that's what it really is. We can skip this. OK, so now since we've seen input-output, let's try to look at a different example, a different language. And the language that we may look at right now is logging. So logging represents yet another language. I might be using word language. Sometimes I might use word algebra, because this is something you might learn if you read blog posts or documentation. So here my language logging represents info, warn, error, debug. And one more time, I have those utility functions that can lift those elements from that language to programs. And one more time, I have to provide an interpreter for that language. So here my interpreter goes from logging to task. And I'm saying what should happen for each of those elements. I'm using, I think, log4j or some other logging library, whatever. And one more time, so I'm just kind of trying to go quickly here, because we're doing the same thing as we did before, just for another language. And I have a program that writes something to info and then writes some debug information. And I can run that program one more time. And let's see what actually gives us. So I have to reload it, because there are some dependencies. And let's run it. So now I have my interpreter as interpreting my program saying info and debug. All right. So you might look at it and you might say, OK, this is nice, but this is just like programming for kids, right? There's nothing really complex here. Where is this ability to write modules? Well, if you think about it, it would be actually a nice feature if we could now write a program that would use both of those languages, right? If we could create a program that would ask something from a user and maybe add something to the logs or whatever. Now the question is how to do it, because we have ability to lift our input-output language to programs. We have ability to lift logging into programs. But how can we write a program that will be using what kind of language is going to be, right? It has to be some kind of sum of those two languages. Fortunately, there is a way to do it. So let me remember. Yeah, that's it. OK, sorry. As I said, it's easier with slides, because I just have to click next, and that's it. OK. So we would like to create some kind of program that would be a sum of our input, output, and logging. Unfortunately, we have a construct which is called, from category theory, which is called a co-product. And if co-product sounds scary, think sum, because that's basically what it is. It's summing two types together. So our EFF type is basically a type which is a sum of input, output, and logging. So what we need is a 3 using that new type we just created, EFF, and giving us the value. Now, the only problem is that if we look at the what we have here so far, is that we're having those little utility functions. They give us a 3 of input output. They don't give us a 3 of EFF or whatever type, right? So we cannot use them. And so what we could do about it? Well, let me do a little bit of magic. All right, so there we are. So now the difference that you guys might see is this. That's that letter S. We no longer have a program that will use language input output. We have a program that uses some language S, whatever that S might be. Well, we get it here, but could it be any S? Well, not really. S is constrained, and it's constrained here. And if it looks scary, what we say when we read this, we say that input output is injectable into S. And that might sound scary, but to oversimplify it, it really means that S is either input output, so it's either input output, or S is a coproduct, so sum, when one of the types that is being summed together is input output. So this constraint here is just telling us that S is either input output or a coproduct where one of the elements is input output. That's all it really is. And all rest stay the same. Like we have ability to lift our input output into program free of S. We can still interpret the language. We can still create programs using it. Nothing changed here. If we look at logging, logging is looking exactly the same. It's no longer free of logging. It's free of using language S. And that S is not any S. That S has to. We need to be able to inject logging into that S, which really means is that S is either logging or S is a coproduct when one of the types in the coproduct is logging. So let's go back to having this machinery here. Let's go back to our example where we try to write a program that is using both logging and input output. Now we have that EFF type that is a coproduct of input output and logging. And we have those two constraints here. One of that was that S has to be injectable into, input output has to be injectable into S, and logging has to be injectable into S. But that's really what EFF is, right? Because type EFF is a coproduct of input output and logging. So this will compile. We can now create a program using language S, whatever that S is, can be anything, as long as it will fit those two constraints. One constraint is saying it needs to be a coproduct with input output. The other constraint is saying it needs to be a coproduct with a logging in it. Fortunately, EFF is exactly a coproduct of input, output, and logging. That's why we can use it. The last thing that we need to do is to write an interpreter, because we need to one more time we have a program that we need to interpret. It would be nice if we could actually reuse what we already wrote, and this is what we're doing just here on line 21. We're taking our existing interpreters. So one that we have for input output, the other interpreter that we have for logging, and we compose them together. And we get the final interpreter as the simple sum, a simple compositions of those two. So then we can we can run it, hopefully. So, free. Sorry, not this one. One more time. 1. What is your name? And we have the name was Pavel. So exactly what we want here to have. All right? Make sense? So in my slides, at this moment, I still have like 20 minutes, right? Awesome. During my slides, at this moment, I had like an awesome picture of a little kitty for your brains to relax. Because like I've seen professional speakers, what they do is they normally, in the middle of the presentation, they tell jokes. Like some of them telling jokes about their wives. I would never do that, especially that's recorded. So I'm a bit scared of my life. But I wanted to show you that kitty for your brain to relax, because what we're going to see, if that was code intensive so far, what we're going to see in a moment is going to be a little bit more intensive. But there's a lesson to it. I'm just hopefully for you guys not to randomly use Twitter at this moment, because try to focus for a minute. Tell your brain it's going to be fine, we're going to be good. Kind of might be difficult to comprehend what's coming in a minute. But let's try to do it. So what I have here is another language. That language is called manipulate account. So I tried to do a language here, like an example that would be a little bit more closer to real world, right? No longer logging all that, but something from the business logic. So that language has verbs like create account, update age, deactivate account, delete account, all that. So for example, create account takes a login and age, and it will give you a handler, where handler is just a type alias for long. And for example, you might call something like fetch account for a given handler, and as a result, you will get an option of that user account you just created. And the user account is here. User account is just login, age, and a flag whether that user account is active, yes or not. Okay? So like one of the programs you might write is to create account for a given login and age. It will give you a handler, and then you might call, let's say, fetch account, which will give you an option of user account, which was just created for you. And we have those utility methods one more time. So we have one more time ability to lift those elements of that language manipulate account to a program, to free. And the last thing we need is the interpreter. And this is where the brain explodes. So we want to write interpreter from manipulate account to something, but it's no longer a task. Why not? Well, because if you think about that language, it's doing underneath 2 things. I mean, more than 2. It will create your account, for example, but then when you call create account, right, that's supposed to give you a handler. So you need to keep an information of what's the current hire's ID. Once that account is being created, you don't return that user account to your caller, you return a handler. So you need to somewhere store your user account. So you need to have the ability to store those elements somewhere. We will be storing them within map. So we're using a concept here which is called state T. How many of you guys are familiar with state? Not many. That's what I thought. That's why I especially chose this example to be a little heavy to comprehend, because don't worry, it's going to be better. I'm just showing what's wrong with it so we can actually fix this. Because if you really think about it, it's not really that complicated. State T here is basically, it takes our state, and our state is a long, which holds current highest index, and the map that has our users. So its state is nothing else, just a function. It takes that initial state, so our current index and that map, and it has to return a new state. Well, it has to return a new state and, well, our handler here. So what we're going to do is we take current index, we add 1 to it, so we get a new index value. We store into our map, we store a new user account with the login and age that was provided here. And then we need to return the new state and the handler, and which, since it's a state t over task, we have to lift that to task. Now, if your brain already is like panicking and you kind of want to see your Twitter because that talk is so boring, bear with me, because I see your pain, right? We just took a little bit more complex example than input output or login, and it's horrible already, right? Because what I really want to do when I want to write interpreter like create account, I want to do probably 3 things, no more. I want to create my user here, and maybe I want to get a new, when I'm creating a new user, I need to also create a new handler, and I need to store that user to somewhere. But it's, the most important part is this. The user account being created. That's all it really is when you create a user account. All of this other stuff, this state, t, task, all this craziness, is a little bit of boilerplate around it, right? It's really hard to see what's going on. For example, if I'm deactivating account, what's the important part is this, setting flag active to false. All the other stuff is just a complex boilerplate that I don't want to see. Unfortunately, there is a way to overcome this problem. But to do it, we need to introduce a little bit of lower level machinery. And let me show you it. Is it here? Sorry. There it is. So I'm introducing 2 more languages. One is called monotonic sequence. And monotonic sequence is yet another language, but has a single one verb in it, which is called next. And next will just give you a next long. So one more time, we have ability to lift that language into 3. And we have an interpreter here that goes from monotonic sequence to ID. So ID is just a trick from Scala Z. So it's a type alias. IDA is nothing as A. If you remember, natural transformation has to go from f of A to g of A. So it has to go to something which is parameterized. But what we really want is just A. What we really want is just the value, is just the logging, the long. That's why we use this trick. But the idea here is that we have an interpreter that will just gives us the next long when we call it. The next language that we're going to see is a language called a key value store. So key value store is a typical like representation of map. You have ability to get a value, to put value, or to delete it. There's no more to it. And one more time, we can lift this into a language. And one more time, we have an interpreter here that goes from key value store, and it one more time goes to that state. So we don't really remove that complexity. Whenever you see some solution in computer science that removes the complexity, they are lying. The complexity is still there. The question is how you handle that complexity. The difference here is that all that manipulation over state is kept in that single interpreter. That interpreter will give us a state monad that will traverse changes over state. But that is all kept in the key value store. Once we have this machinery, we can write our programs a little bit better. Sorry. Okay, so Sorry for that. So what we want to do is we want to write a new interpreter. But this interpreter, so remember the previous interpreter that we had was just going from our, it was here, from our manipulate account here to craziness, right? We want to remove the craziness. So the new interpreter will look like this. So it goes from manipulate account to free. So you might be thinking, wait a minute. I have a program that is using manipulate account. It's supposed to be interpreted to something that I can run, and I'm getting free back. That's a little bit crazy, right? Well, think of your Scala code that you compile. Does it compile to assembly? No, it compiles to bytecode, right? We have a lower level language that can be interpreted by something else, by JVM. So here the idea is pretty much simple. We have a higher level language, like manipulate account, that knows all your business logic, create account, deactivate it, remove it, fetch it, whatever that is. And you're taking that higher level language and you interpret it to a lower level language. So here we are interpreting that language, interpreting into a program that uses using some language S. Can it be any S? No, that S is constrained. We are constraining it, one more time, by key value store and monotonic sequence. So we're saying S can be pretty much anything as long as S is a coproduct that has both key value store and manipulate account. Okay? So it can be any S, can be more, can be coproduct of a key value store, monotonic sequence, and task, and whatever other stuff. But if you have those two, then we're good. Then S is fine for our program here. And now our interpreter is amazingly easier to comprehend, because create account, well, you just called monotonic sequence next, and you get the handler. And then you create a user account and put it into key value store. When you deactivate account, well, you fetched that user by that handler, so you get a maybe user account. And depending on whether that user exists, yes or not, let's say it does exist, then you just change its flag active to false. And that's what it is. So why is it really cool? Because some of you guys might look at those examples and might be thinking, there's a lot of boilerplate happening. Like I understand modularity and all that, but there's a lot of code being created here in the simple examples. But think about it for a minute. If we have those different languages representing our higher level concerns, like authentication and manipulate user account and some other stuff, and then we will all interpret them to lower level languages, where those lower level languages, they still need to be interpreted, right? We still need an interpreter for those lower level languages. But the difference is that you write interpreter for the lower level languages once. You once will write interpreter for key value store. You will once create an interpreter for monotonic sequence. So then you can write your higher level interpreters with ease, with just reusing the lower level language. And you already have all the machinery written for you, because once you do it, it's there in your project, and you can reuse it among other projects and all that. I have like 5 minutes left, so I'll be not showing you all of it, because I'm sorry, I had slides prepared, but didn't realize that the font might be too small. But the repository is there, and if somebody is interested, there's an example here, the final example, that has our initial program. I'm just going to skip through it very quickly. So it has our initial program here, has the final interpreter that goes from EFF to free of S, where S is constrained by key value store, monotonic sequence, and task. Why that is? Because we are using both input, output, and manipulate account. So manipulate account is constraining our lower level language with key value store and monotonic sequence because it needs those two, while input output needs a task as a lower level concept. So once we have that interpreter, which we basically create by summing existing interpreters together, the only thing that we need to provide is an interpreter that will go from this lower level language to our final task. And this is something that once you implement this, your final interpreter, so your final thing that will go from EFF, just a reminder, EFF is this co-product of input, output, and manipulate account. So your final interpreter that will go from EFF to task is just a composition of this high-level interpreter and lower-level interpreter. And that's really what it is. I'm having like 4 minutes, which we're probably going to miss. Maybe we'll have a moment for one more question. Somewhere here is my kitty. I'm not going to look for it. Just to sum it up, it really took me a while to find a cute kitty. Shame. Anyway, so you might ask, all right, this actually looks like a nice theory. It kind of looks a little bit academic. Is it really usable? Can I write software? So I've been lucky enough to work for a company which uses free extensively. The product is open source. So if somebody's interested, you can actually look it up. Maybe ask me a question after this talk if you're interested. And we use free to the very extent. And for me, when I joined the company, and everything was complex at this point because the domain was complex and all those different functional programming stuff, and it was just overwhelming. They gave me just this little algebra here. Open file, write to a file, close a file. And they just said, focus on this stuff, because I was writing a connector to Apache Spark. Just focus on this and forget about anything else in the code base. And this was brilliant, because I could write all those interpreters. They could fail. They could destroy the whole thing here. But that was all encapsulated. I could never break anything outside. And once I had this, they told me, well, you had that, awesome, forget about it. Now implement this algebra and that algebra. And at the very end, one guy showed me, one of my colleagues, look, check this cool trick. And he composed everything together, and it worked. I was like, holy cow. That was just amazing, because I was, for the past 2 months, I was just focusing on those little things. When I was doing write file, I never thought about querying file. When I was actually writing queries, SQL queries, I already forgot about what I wrote a month ago. But once those things were written and they were tested, it took us 50 minutes to compose everything together, and it was working from day one. And if that's not what we as programmers strive for, modularity, pure modularity, then I don't know what is. If that was complex talk, I don't expect everyone to understand everything what's going on. But I just want you guys to be a little bit inspired that software development might be done in a way that's a little bit closer to engineering than what we normally do, where we just hack things together and see if it works, and if it doesn't work, we just ship it. It can be done better, and free is one of those ways to do it. I'm not saying the only way, but one of the ways to do it. If you have questions, I'm happy to answer them, but I just should end right now. Thank you very much.